to 1. Sorry. Oh, sorry. Okay. So how to use? So this dendrimer structure, dendrimer should be the better candidate of the particles used for non-filtration membranes. So based on this design, we prepared the source of the non-filtration membranes with different charged state and so on and so on. This is a simple process to prepare the non-filtration membranes using the interface polymerization process. So in our work, we just use the PSF ultrafiltration membrane as a support ultrafiltration membrane. So this structure we use the dendrimer. This is the dendrimer. In 1 molecular weight have about over 100 amino groups outside the molecular weight, the dendrimer. This amino groups should be polymerized with the TMC and so on. So in our works, we checked the different composition using the dendrimer and the PIP as a copolymer, and prepared the sorts of the membranes, NF membranes. From this figure, we can find that if we use the amino-based PAMA-based dendrimer, the flux and the permit and the rejection is very good. It means, so especially the flux is very high. If we use some that PAMA to replacing PIP as a monomer. So this means the flux should be improved very effectively. Why the NF membrane have a higher flux? This is a mechanism. So this means in this dendrimer, many pores should be contributed as the water permission channels inside the molecular weight. So no matter what salt solution used, the flux should be improved for all the solutions. So this work suggests, so the dendrimer should be a proper nanoparticle for the 3M membranes to realize the higher flux. So flux is one consideration for non-filtration. Another consideration is to improve the selectivity. We know many non-filtered membranes are charged membranes. How to realize the charge state of the non-filtration is a challenge. In our work, we start from the amino-based PAMA. So we can convert the outer aminos to different charged state. For example, this is the cationic state, and this is the anionic state. So it's very easy to convert the PAMA to different charged state. If we can think, if we using this PAMA to prepare the non-filtration membrane, the membrane should be charged from the this charged PAMA, the PAMA state. So this composition used for to prepare the non-filtration membrane. From the potential data relatively charged. So this is the structure characterization. You can find the state and the charged state of the membrane. So the water is very effectively realized. So this is the structure of the membrane. So we can find the PAMAs distribute in the interface polyamide layer. So and the distribution is very homogeneously, very homogeneously. So this is the process of the non-filter membrane, non-filter membrane. So the process ranged from the 0.4 to 1 nanometer. So this is the process. So from this figure, we can imagine what is the water permeation route and what is the water permeation route. So in this structure, we can find the water can permeate through inside the pores of the perma, and also the water can permeate through the interface pores. Interface we call the interface between the particle and the matrix. So two water permeation flux route. This two permeation route will yield higher water flux property. So from the measurement, we can find the So because this membrane could be charged in cationic and ionic state. So for the separation of selectivity property, we can find from this. If the membrane is charged by the cationic state, means positively charged the non-filter membrane. For the higher cation salts, the rejection rate is very high. It means the electric repulsion property functions for the higher separation of the magnesium chloride, So for the ionic or negatively charged membranes, so the rejection of the higher sulfate salt is higher. So this result suggests so we can effectively prepare the charged membrane to separate different ends. For example, chloride, sulfate, or not, sodium and magnesium salt. So this is the mechanism of the why the membranes have higher selectivity for sodium and magnesium. So for property comparison with the other reports, we can find the property very high. This top position means this membrane should have higher selectivity and permanence. Also, this membrane have very good stability. For the longer filtration time, the rejection and selectivity and permanence is very stable. So for the membrane with different charge states, the separation between the chloride, sulfate, or sodium and magnesium is very high and stable. This separation factor, right? Separation factor is very high compared with the other reports. So this means that this suggests that the charge non-filtration membrane should be effectively prepared by the perma-based dendrimer. But however, for the we select the positively charged non-filtration membrane to membrane and investigate the salt separation property in detail. So this is the data potential of the positive charged membranes. This membrane showed very high positive charged state. So also this is the distribution of the perma in the polyamide film, and so this is the positive charged state. Okay. In the polyamide layer, in the bottom of the polyamide layer, there exist many porous structures. This porous structure will contribute to the higher flux, and okay, this is the effect of the membrane used for separation of the mixed inorganic salts. In the ever reports, many researchers just use a single salt solution to investigate the salt separation property. But in our work, we use the mixed salts, and we found also this membrane have the very high separation ion separation property for the anionic or different ionic states with different ionic states. So we know from the result above, we can find that PAMA should be very good candidate to prepare the non-filtered membranes with higher flux and higher selectivity. But we know PAMA is relatively difficult for preparation in large scale. If Amin X application, we need to get the simple and the nanoparticles easier to synthesis and lower price, lower cost. So besides the dendrimer, we have another kind of polymer with nanoparticle size. It's called hyperbranched polymer. So we prepared the series of the hyperbranched polymers like this. We are in this route. Compared with the dendrimer, though the hyperbranched polymer have have a similar structure, but very easy to prepare. So we using this hyperbranched polymer to replace the dendrimer to prepare the different non-filtered membranes with different charged states, and also realized that charged non-filtered membranes, this structure of the non-filtered membrane in hyperbranched polymer, and the property indicates that the pore size also ranged from 1.5 to 1.1 nanometer. So this is nanometer, the pore size, and also charge state should be also controlled very easily. The flux also very much higher than the non-filtered membranes not containing the hyperbranched polymers. This is the separation property of the different salts for hyperbranched containing non-filtered membrane. This property is similar to the PAMA monomers. So this result suggests we can also using hyperbranched polymer to prepare the the non-filtered membranes, and this hyperbranched nanoparticle should be prepared very easily in large scale. This characteristic we just asked, we can using HB hyperbranched polymer to prepare the novel property non-filtered membranes, especially for ion separation and salt separation. So briefly, from the discussion above, we can conclude that dendrimer, amino-based dendrimer, the research on the dendrimer-based non-filtered membrane suggests a new route for charged membranes, and to overcome the higher expense of the PAMA, we can use a hyperbranched polymer in practical application to prepare the applicable non-filtered membranes, because the hyperbranched polymer could be prepared via one-step polymerization process. So this is our work about the non-filtration membranes based on the hyperbranched and the PAMA polymer nanoparticle. So This work is supported by the several projects. But one project is of the cooperation project between China and Egypt. So with some work was done by us and Dr. Hiba together. So thank you very much. Thank you much. Long time we don't give presentation in English, so not very. My presentation may be very poor. Sorry, and thank you.
Professor Mariam Sarko, she is a doctor engineer in therapeutic company, Germany, professor of environmental process engineering at College University of Applied Science, head of the Department Surface Technology at Applied Research Institute for Steel and Process Industry. She has more than 15 years of experience in filtration and material technology. She will speak about membrane filtration and flat sheet membrane technology. This
Shaban, Assalamu alaikum. Good morning. Thank you very much for the opportunity to attend this conference again. Professor Ahmed, Shaban, Professor Eba Abdallah, Professor Shereen, Kamel, Amin, thank you very much for this invitation again. Shukran. The 2019 conference was a great experience for me, and I'm so happy and grateful that this contact was settled and first joint projects in research started, even in the struggles of the pandemic. My lecture today will be a combination of showing latest results of therapeutic process developments and things on ceramic flat sheet membranes, and also general aspects on membrane technology. Since 1st of August, I am professor for environmental process technology at Cologne University of Applied Science. And at the beginning of this conference, I would like to align all of us on some membrane basics before you all start into the conference. And I thank Professor Chu very much for this very interesting presentation on the nanofiltration membranes. You will see what I prepared is a little bit different, and it's in addition to this work. I want to show you the filtration spectrum we're talking about in membrane technology. And well, this picture starts with sand filtration or even other filtration technologies, and then it moves with more tinier and tinier pore size over microfiltration and ultrafiltration to nanofiltration reverse osmosis. Therapeutic filtration is in the range of microfiltration and ultrafiltration, and this is here in the pore size of 0.05 to 0.5 micrometers. I will not talk about nanofiltration and reverse osmosis because the separation techniques and the separation modes are different compared to the pore membranes. What I will focus are filtration systems which can remove particles and molecules. And in brackets, you see here the ions. Ions are normally removed by nanofiltration and reverse osmosis systems. And we will see at the end of my presentation that it might also be possible to remove ions by ultrafiltration systems. When we look into the porous filtration systems, which is a core part of my presentation, we can divide them into the deep bed filtration systems you see here on the left-hand side, where we have big particles and they are rejected in a filter bed, and sooner or later these particles might even move through this filter bed. On the other hand side, we have the surface filters, and membranes are typical surface filters where particles which are bigger than the pore size are rejected. What I want to do now is to go with you through some core terms and definitions and some aspects on membrane materials and membrane processes, because I know that many of you are either developing new membrane processes or new membrane itself. And this is just some thoughts on the differences between all the membranes and the processes available, and having a look at advantages and disadvantages. What we are always talking about is the transmembrane pressure for all pressure-driven membrane processes. The transmembrane pressure is a driving force between the differential pressure on the feed and permeates. On the other hand, we are always talking about the flux. The flux is a term used to design the filtration step. It shows the capability of the membrane transferring the liquid through the membrane area. And when you combine the transmembrane pressure with the flux, you have a wonderful value for comparison of the performance of different membrane systems, because you combine not only the volume of the liquid, you combine also the membrane square area, the time, and the pressure. And with this number, you can always combine different membrane systems. Finally, also interesting is the recovery rate, which is a real flow capacity without losses. This means all the backwash water is already integrated in the recovery rate, and you have a calculation tool to see the efficiency of your membrane system. When we look at the filtration and the filtration permeability and the processes, we have two basic filtration modes. We can run such a system in a pressure-driven mode. This means we give a pressure, and then during time, because we have particles on the membrane, this leads to a decreased flux. This is a not so typical system for water and wastewater treatment. This is more done in biotechnology, because you have often very pressure sensitive systems, and there you decide to have a pressure like 2 bars, and you do not want to increase over this pressure. In water and wastewater treatment, you often operate with flux driven systems, where you say, I want to clean 1,000 cubic meters per hour, and then you design your plant with this flux. And during the filter cake formation, this leads to an increased pressure, because you need more pressure to press the water through. Both filtration modes result in decreased permeability. And you see this on the picture. You have the permeability over the time, and without any backwash, you will have a decreased permeability over the time. To operate such a membrane system with higher permeabilities, you run it with regular backwashes, and then you have higher permeability. Nevertheless, permeability decreases a little bit, and from time to time, you all know that we need a chemical cleaning. The question is, what is causing this chemical cleaning need and even this backwashing? We see that each technical membrane process shows a change of its performance. We have either a change in the performance of the selectivity or the permeability. The reasons are concentration polarization or absorption of solids on the membrane, scaling and fouling processes. And the control of these performance losses is one of the very important points in process development, in process running, and especially in the membrane material development. And I know that there's a lot of focus towards this conference on membrane fouling and how to avoid membrane fouling by process development or material development. Just to give you an insight what is happening inside the membrane. When we're talking about scaling, you see this scaling is a precipitation of inorganics, salts and hardness, and you see here inside the pipes that scaling occurred. And this is the same thing what happens inside the small channels of the membrane. Fouling is the absorption of organics and microorganisms. inside or on the membrane. Mainly this happens on the membrane. You see here this biofilm on a sensor, and this is happening on a membrane, and then water cannot move through the membrane anymore. And you need strategies to control this fouling, to have high performances of your membrane. When you're producing membranes, you're forming somehow pores to reject particles, microorganisms, or molecules. And then you define the pore sizes of these membranes. And this was shown by Professor Chu very nicely, how to arrange pore sizes and how to activate membranes. And when you have a very sharp pore size, like you have it here with a black curve, very, very narrow pore size, then you also have a very strict cutoff, a very defined separation. This might be especially interesting when you want to harvest specific molecules. When you have a more or less diffuse pore size, like this very broad pore size, you have also an undefined separation. And while you develop materials, you always have to ask yourself, what is necessary? What is the target of my membrane development? I also want to show you different types of membranes, and I know that this picture is not giving the full picture of all types of membranes we have. We can divide the membranes by the external structure, the membrane shape. We have flat sheet membranes. Flat sheet membranes in polymerics are often spiral wound, and you have the spiral wound modules NRC, for instance, is also producing. We can have pipe membranes, and we can have the shape of hollow fibers. When we go into the internal structure and morphology of such a membrane, you see here's a core difference of polymerics and ceramics. The polymerics are more or less finger-like, with here is the active layer and here's the body of the membrane, finger-like structures with the pores going through this membrane where the water has the channels. And for the ceramic membrane, we have another filtration direction on this picture. We have the separation layer here. And you see that the ceramic membranes consist of a lot of small particles, and these particles are sintered together. You have a totally different behavior of these membranes. And I summarized it here, the pore morphology of polymeric membranes and ceramic membranes. You see a lot of different materials, and I want to focus on the core differences. When you see this finger-like material in the SEM picture of the polymerics, you see that we have comparable short pathways, and we have a comparable dense layer on the surface where we have very tiny pores. And polymeric materials are like a sponge. They are sensitive to pressure, high pressure, pressure changes, because you can press them like a sponge together. And when you increase temperatures, these materials become weak and the pores can grow. And even larger particles may come into this membrane and enlarge the pores due to this growing of the membrane pores with increasing temperatures. Those polymeric membranes are sensitive to material aging. Ceramic membranes are constructed out of small particles, which are very hard and you cannot compress them anymore. You see here much bigger selective layers than you have here with the polymeric membrane. You have longer pathways for the water. You have a lot of very tiny particles sintered together, and the ceramic membranes are insensitive to pressure and pressure changes. You cannot compress them. They are insensitive to temperature. They will not enlarge, and they are more or less stable against chemicals. And so you have two completely different materials when you talk about polymeric membranes and ceramic membranes. When you go into the operation mode of different materials and the filtration of membranes, you have filtration in to out. The into-out systems are installed in closed modules and you have almost no tolerance to solids. The solids are inside the module and you press the water out, and here cake layer is not desired. You know it especially from reverse osmosis plants that it is very sensitive to particles and you have to remove them before. The filtration system out to in is another system. You install those membranes directly in the tank and you have no limit of solid concentration because you suck the water inside the membrane and the dirt, the particles are staying outside those membranes and you have no limit of cake layer. And this is a complete different operation mode, and you also have to decide what you want to do, what is the target of your filtration and your material development. When I come to the ultrafiltration by the flat sheet membranes, this is the core work of the technology development at CeraFilter. These filters are working with an active filter layer outside of the ceramic flat sheet membrane. The suspended solids are rejected outside the membrane and the clean water is sucked into the membrane and transported by the end caps out of the system. When you ask the question, what is the idea of ceramic flat sheet membranes compared to the standard systems you know from the tubular pressurized membrane systems, this is summarized on this slides. And we started the comparison with the sand filter. And why did we do this? Because open sand filters can be replaced by ceramic flat sheet membrane modules. Due to this compact design, you can have a up to 5 times smaller footprint and you can increase the water production capability of sand filter systems.
Yeah.
You have a real disinfection and physical barrier for germs and bacteria and about 100 times smaller pore size. The ceramic flat sheet membranes are...
We have to move. Yeah, just 1 minute. I'm sorry. Actually, I have kind of today, so just 1 minute to conclude. Just 1 minute to conclude, please.
Yeah. Yes. You have, I want to show 2 more slides, please. You have to work with the polymeric, you have insensitivity against the formed filter cake and against high temperatures. And you can submerge those systems into open tanks, and this is a very easy system, and you can work with those filter cakes. And this filter cake formation is very important and a very clever system where CeraFilter developed a new type of process. And I want to show it on these 2 slides. During the pressurized systems, you have the compression of the filter cake, and with the suction pressure at ceramic flat sheet membranes, you have a very loose filter cake, and you can use this filter cake as an additional filter barrier, and you can improve the water quality. This filter cake can be used as active filter cake or just filter cake combination. The filter layer, cake layer filtration combines the precipitation, oxidation, or flocculation processes, and you can remove iron, manganese, and TOC. With the active filter cake, you combine filtration processes with the adsorption processes. You have the selective removal of dissolved contaminations such as ions, molecules, and organics. And this is why I said in the beginning, together with this active filter cake filtration, you can even remove molecules and ions with ultrafiltration. And on this final picture, I just want to show you that the removal of trace organics is possible with a combination of active filter cake filtration and ultrafiltration. The bed volumina was increased very much compared to granular activated carbon systems by this filtration system. So finally, all membrane systems, and I'm really looking forward to this conference, will improve the global water challenges by development of new technologies, new membranes, and new processes. And I really want to encourage you to experiment with all these new processes. Thank you very much for your attention.
Thank you, Professor Mariam, for your presentation. If there is any question.
Hello, can you hear me, please?
Yes?
Yes. Would you please clarify for us about your last filter, which you show us, cake filter? How many times it can be durable, and how we can remove the dirt or the waste from it if we can use it for many times? And what about its efficiency by time? Thank you.
Yeah. Especially the cake layer filtration is something, it's different compared to typical membrane filtration, and it's different to granular activated carbon systems. When you go to a granular activated carbon system, you have a big tank and you're filtering for half a year or about 1 year to absorb the molecules on the activated carbon system. When you use membrane system, you filter, have your backwash and your cleaning. And the difference is now that we use powdered activated carbon. So we have a very high surface area of the activated carbon, and we bring a very thin layer of about 2 to 3 millimeters of powder activated carbon on the membrane, and we can reject this powder activated carbon by the membrane. We filter for about 12 to 24 hours through this thin activated carbon layer, and then we make a backwash and reject completely this activated carbon. We found out that sometimes you can reuse this activated carbon a second time, but normally you discharge them after this time. And the increase of the bed volumina is up to 10 times compared to the granular activated carbon system, because what we think mainly is this, that we can use this extremely high surface area of the powder activated carbon. And because we bring this powder activated carbon layer on the membrane, we have a very big surface area, and all water and all molecules needs to move through this layer, and therefore we have a very good absorption.
Okay, thank you.
Thank you, Dr. Walid, Dr. Mariam. I am so happy to meet you again this year, and I hope you talk with us every year. Thank you, Ms. Dr. Mariam. Thank you again, and goodbye.
Thank you.
Dr. Fan, good morning.
انا ببعت لللينك. كنت في مشكله عند الصوت.
Yes, ma'am. Oh, You can read again, start from the beginning. You can read and you can start from the beginning. If you hear me.
Surface property, different from the organic foulant. The bacteria can not only attach on the surface, but also can grow on the surface. Moreover, the dead bacteria also, as well as the cell matrix, become another type of organic foulant which cover on the surface. That will block the pore size. So it's important to reduce the foulant absorption and also avoiding the bacterial growth to decrease the membrane falling. Actually, there are many types of the membrane falling modification strategies. Here, I won't introduce in detail, but then how to prepare the antibacterial and falling membranes. Actually, roughly, I divide in two types. One is using the same components, and another one is using the different components. For the first one, the silver nanoparticle or silver ions, graphene, also copper are always used. But for the second time, the researchers construct two functional layers, including use PG, beta CD, Zwitterionic copolymers to prevent organic falling, and using some drugs, copper and quaternary ammonia to reduce the biofouling. In our research, we tried to build a combination of quaternary ammonia and Zwitterionic copolymer for proved antibacterial and fouling property of the membrane for sustainable application. One strategy is controlling the quaternary ammonia groups and the Zwitterionic groups to controlling the composition to get the antifouling and antibacterial property. Another way is we're using the charged polymers to get the mixed charge polymer and to regulate to get the antibacterial and antifouling layer by regulating the charge and the composition. Here I will introduce three strategies we use to make the antibacterial and antifouling membranes. First one, we creating the inner quaternary and outer Zwitterionic layer for improved performance. In this method, PVDF and the PMD membrane was prepared by the NIPS process. But then PMD is a kind of a polymer that is containing the tertiary amine. Then the membrane is quaternized by the PCMS. Here, PCM not only we can quaternize get the quaternary ammonia. Also, we bring the double bonds onto the membrane surface. Then third steps, we're using the radical polymerization on the membrane surface. We bring the Zwitterionic monomers onto membrane surface. Then we can make that the inner surface is the quaternary ammonia and outer surface is the Zwitterionic copolymers. Here the characterizations for the FTIR, we can show that we can show from the 989 centimeter, we can find the quaternary groups by the second step. We also can find the from the 1044, we can get the we can confirm the sulfonic acid group from the third step. So from the FTIR, we can get that our preparation is succeed. And also from this figure, we can find that is a PCMS participate in the polymerization of Zwitterionic monomers on the membrane, which can improve the surface stability. From the XPS, according to the wide scan and the core-level nitrogen signals, we confirm that the sulfur and also the quaternary ammonia group. We can, according to this result, we can calculate the graphing degree of SBMA was about 0.3 microgram per centimeter square. Then we calculate the surface charge. Actually, it becomes much more weak positive charge, and it becomes more hydrophilic because we introduced the Zwitterionic polymer, and also the surface pore size become reduced because of the surface grafting process. Most important, another we can find, although the pore size decrease, but the hydrophilicity increase. Actually, in the final membrane, the water permeance of the final membrane increased. Then we using the protein static adsorption experiment. We found after our final membrane, we can get very low BSA adsorption, and we confirm our results also by the filtration experiment. Then we conduct the membrane in using some bacterial suspensions. One is in Ceres and another one equally. We can find that all the surface on our membrane with the Zwitterionic and the quaternary, they have a few the Q rate is over 97%. That means that our membrane have a very broad antibacterial behavior. And in this figure, we also found that after we soaking this membrane in the bacterial suspension for 2 days, after quaternary process, there are many bacteria accumulated on the membrane surface. But in our the surface with the Zwitterionic, we can find only few dead bacteria foreign attached on the final membrane. From the result, we can find that in the quaternary ammonia and outside the Zwitterionic polymer, the on-UF membrane was succeeded constructed, and the membrane showed very excellent and antibacterial and antifouling property. For stage 2, I introduced that in development of the membrane with well-dispersed polyampholic copolymer via a composite coagulation process. Here we give the preparation process. That the composite coagulation process means that our copolymer, we put the polyamphilytic copolymer in the coagulation base, and we introduce. That means our polyamphiphilic copolymer can introduce deep side of the matrix. Actually, it's very different from the traditional surface coating. And this one, this the polyamphiphilic copolymer can be well dispersed in the membrane matrix. We characterize the surface hydrophilicity to degrees even lower than by the coating method. We also we characterize the surface charge. For the original membrane, it's very negative, but for our membrane, we can the surface charge is very neutralized. For the water permeance, much higher for the original membrane, and also for the BSA filtration, we can find that the water, the flux retention or total recovery is much higher than the original membrane. In this research, we carefully studied the membrane matrix. We use the eye attention attached measurement. We use the organ to peel the surface surface in the matrix. Actually, we found some very interesting phenomena by the membrane made by the coagulation process. We can find even we use 1 or 5 times H, with the membranes shows very similar compositions, but for the membrane made by the coating method, even after 1 time iteration, we find the surface composition changed well. That means the copolymer is just attached on the membrane surface by the coating, but if this of the polyamphiphilic copolymer exists in the membrane matrix and dispersed well. It's so actually our membrane that means our membrane have showed a very stable performance compared to the much more stable compared to the coating method. So we can get to the conclusion that the composite coagulation process is expected to provide a novel fabrication method for modifying membrane to achieve very excellent permeability and antifouling property. It also expects to overcome the processability problem of the polyamphiphilic. Let's move to this next. We introduce the strategy 3. We using enhancing the antibacterial and antifouling property of the polymeric membrane using surface charge regulation. Here is the route 1. That means we have the route 2.
على الببليكيشنز هتلاقي الببليكيشنز بتاعتي افتح اي ببليكيشن وخد زي ما مكتوب. واضح؟
Okay. So I introduced the route 1. That is we grafted the positive charge monomer onto the negative charge surface via the UV radiation. The surface charge is regulated by controlling the substrate composition and surface grafting conditions.
عامة تسيب الورق مع ايمان.
We first we also characterize the water contact angle, and we found that the membrane become more hydrophilic. Then also we found that we tested the underwater oil contact angle. We found the membrane become super oliphobic. Then also we tested the surface charge. Actually, you can see the surface charge is also neutralized. That means it had a high potential for antifouling actually. Then we also using the protein adsorption and also the bacteria adsorption. We can find after the surface grafting, the adsorption is very low, and we also try to find the bacteria on the membrane surface after attaching. We can find for the original membrane there's many bacteria soft on membrane, but there's always no dead bacteria on surface. But for our membrane, for our modified membrane, we can find there are few bacteria attached on the surface, but all the bacteria have been killed. So that means our membrane have a very good antifouling and bacteria property. And now we also use the membrane to do the filtration experiment. We can find for the BSA solution and the oil water emulsion, the water flux maintained very stable. But for the original membrane, the flux decreased sharply. Also, we found that if we use our membrane, we can get very high water flux retention. Here we have some explanation. Because of we introduced the MTIC onto the membrane, the hydrophilic component further improves surface hydrophilicity. Meanwhile, MTIC neutralizes the surface charge. In addition, a polyphotic copolymer was formed. Such a copolymer was recognized as an antifouling component. Therefore, a more hydrophilic and a non-charged surface containing a polyamphiphotic copolymer was formed through a simple surface grafting method. Another reason that the low bacteria adhesion on the modified membrane was the antibacterial property of the ammonia groups on MTAC. This property effectively prevents bacterial growth after the surface adhesion. So here I also introduced the rule 2. We have the similar strategies, but we use the positive charged surface and the negative charged module on the membrane. Actually, we can also get the very low protein adsorption and a very high bacteria killing rate. Here are the conclusions. From our research, we successfully make the membrane with an inner quaternary ammonia and outside Zwitterionic copolymer layer. And also we make the membrane with a well-dispersed polyamphiphotic copolymer via a composite coagulation process. Then we can make the membrane antibacterial and antifouling property membrane by the surface charge regulation. Our membrane show very excellent antibacterial and antifouling property, which is a potential for complicated water treatment. Now we thank for the some fundings, also Professor Zhu and Professor Matsuyama, and also we'll thank 2 students, Dr. Wang and Mr. Zhu, for their contribution. Thank you.
Thank you, Dr. Ahmed, for your presentation. Yeah.
Dr. Mahmoud Mubarak. He is researcher of clinical chemistry, Department of Petroleum Music, Zwitterionic Research Institute in Egypt, lecturer at the Faculty of Science, Mansoura University. He is publishing more than 63 research papers in the field of desalination and treatment and the preparation of nanomaterials. Dr. Mahmoud.
Hi, good morning.
Good morning.
First,
Good
yes.
morning.
Good morning. I would like to thank the conference organizer, Dr. Ahmed, Dr. Heba, and Dr. Shereen, for their effort to make it and appear in this honorable view. My presentation, as you can see, it is a work built from a project funded by STDF in the last of 2020. It is concerned with the problems of iron and manganese associated with the hardness and higher salinity of aquifer in Upper Egypt and its bad feedback on the RO or membrane system. It is under title of Modified Zwitterionic Nanocomposite for removing of heavy metals and hardness from underground water in our system, hybrid system, and reduction of membrane fouling through column absorption pretreatment process. I will talk briefly about the problems of ion exchange and absorption and problems of iron and manganese and hardness in the underground well, and briefly, and its a problem associated with the RO system. Also, I will talk about the composite that we built in our project for the removal of these ions and the metals and its effect on the RO system. First, as we know, that is some or many of underground well suffering from iron and manganese with higher concentration associated with hardness, and the excessive drilling or suction of the water increasing the ability of many biological and chemical problems associated with this water during the treatment process, where some wells having bacteria like SRB bacteria and some other salts that like iron sulfide that when precipitate on the membrane, it is destroyed it and decreasing its lifetime with time. And we are facing this problem daily with companies working with well having a high concentration of iron and manganese, and also in the Upper Egypt as discussed in this our project. So we must deal with these problems associated with hardness to reduce the bad effect on the membranes during the desalination process. Also, as we said, it is a serious problem mainly facing membrane system during the desalination or treatment process using RO membranes. Even the water can with SCDI less than 5 and concentration of iron less than 0.1 milligram per liter can cause many problems and accumulate for the inorganic and organic scale on the membrane and leading to successive cleaning and replacement at the end with new another membrane and so on. So the cost increase for the treatment of this type of water. Also, it is agglomerated with the organics present in the water during the desalination or treatment process and helping in agglomeration of these materials, even its bacteria or organics, and accumulate it on the membrane fastly and increasing the rate of cleaning of the membrane. Overall, the performance of the system and the flux reduction with time in the any system of membranes, RO or nanofiltration membranes, and so we need mini cleaning all the time. So the membrane life destroy, decrease, and the oxidative damage for the membrane with time is increasing, and so we need with time replacement for the unit every day or every month after it expected by the engineer or the companies that company sharing this membrane from them. They said to them it is 5 years. They found it is not complete 1 year in some wells and some locations. There are many processes for treating or removing of iron and manganese from water. It is like ion exchange and biological oxidation, catalytic oxidation, and direct oxidation, but all this process suffering from prion concentrated with manganese or ions and that helping in the production of bacteria and growth of bacteria and algae, and this produce another problem with the system. The ordinary or the normal treatment process found in the Upper Egypt, depending on the oxidation precipitation process, simple process, depending on adding of coagulant. After that, oxidation of the iron and the manganese by air and chlorine sometimes. After that, disinfection by chlorine and filtration was sand and pump this water to the people. But we found that this water come to people, as you can see, the right bottles, it is the fed water to the treatment unit. But the left one, it is the water that has come to people. It is the opposite thing that take place in this village in Asyut. So our target, it is decreasing using RO or nanofiltration membranes for desalination of water having a high concentration of iron and manganese by using a pre-treatment adsorption process, not ion exchange only, but adsorption, having all the mechanisms take place with higher affinity and higher capacity to overcome the problems that take place for the membrane and increasing its lifetime with time during its work with this type of water. Hybrid system, as you know, it is a combination of 2 or more processes, like nanofiltration with RO or distillation with membrane process. It is mainly, as we know, and the famous one is the distillation and the membrane process. But if we're talking about adsorption, we found it is all time we hear adsorption cooling, silica adsorption, solar adsorption, but not hear about chemosorption or membrane or chemosorption membrane process, combination of this process. Adsorption is a accumulation of molecules on the surface of certain material, having its affinity to absorb this material. So absorption having a many advantages, like high performance and low cost, and the wide pH range. So it is not need to change the pH during the application of this process and the treatment of desalination process. This advantage is the waste products, but it is overcome with time. And the selectivity here, we produce a material in our project or our paper having a high affinity toward the many materials and with high affinity and high capacity. So combination of different mechanisms, chemical mechanism, absorb the material for material ions in the water, even it is heavy material or hardness, and the sum of salinity. It is will not increase the salinity as we see in the ion exchange or softener, as the engineer know. So in our lab, we prepare a new composite material called composite titanate nanocomposites from natural source, cheap natural source, kaolin, and treating it with hydrothermal method to produce a new self-assembled structure having a high affinity and high capacity for different ions in the fed underground water. And to characterize this material, as we will see, first, the characterization of the prepared nanocomposite material like zeolite, titanate, or zeolite A, and kaolin. As you can see, there is change in the peaks of identified material and kaolin, and there are many peaks for hydroxide groups, hydroxide groups at 3,000 and 1,500, and also there are for SiO at 100, also 1,000. Also in the XRD, we found the main characteristic peak of titanium dioxide at 25. If we're looking for ECM, we can find a huge change in the material or natural materials that we made in our lab. First, on the left, you can see the ECM of kaolin. As you can see, it is a flat sheet, compact flat sheet like book with small surface area and low active site. But if we converting it to zeolite 4A, it is from a cubic structure with a small surface, but with modification and the production of self-assembled zeolite 4A titanate or titanium dioxide. You can see a regular structure with different pore size and the pore distribution in the main bulk of this material. So it is give different active sites on the surface, so different affinity with different mechanism or chemosorption mechanism. In the TM, as we can see, is a kaolin on the left, having a second structure with flat sheets, smooth and transparent, but with modification. First modification to zeolite 4A, it is having a mini pores and a regular structure, and here we can see the distribution of the titanate in the zeolite 4A. To be applicable this material, we must do some adsorption experiment to study its affinity and its capacity for the target ions in the fed underground water. A batch absorption study to optimize the parameter of this material is done using a pH, different pH. We work on different pH. As you can see, that is titanium dioxide inside the Zwitterionic 4A for our composite having a higher affinity for the removing of ions, iron and manganese. And after that, come below it, the Zwitterionic 4A also at a hardness study and the calcium removal. We found it is a superior also our composite material having a maximum removal efficiency reached to 100%. Also in studying the dose effect, we found that is 2 grams of our composite or natural composites having a high affinity increasing with increasing the dose due to increasing the active site and the functional group present on the adsorbed material. And the same option or behavior appear in the study of the removing of hardness from the fed underground water. Also, the effect of time, we found that it's increasing the time, increasing the absorption and the removal efficiency of iron and calcium and the total hardness. We found the maximum time between 20 to 50 minutes, and this is very short time, leading to production of high volume of treated water that is helping the RO system or non-filtration system to work continuously without stopping. Also, the mechanism showing that theoretical modulating for this adsorption process, showing that the adsorption is chemosorption reaction depending on the complexation formation with metal in the feed water. Also, the effect of initial concentration, as you can see on the iron and the manganese removal or total hardness, it is found it is increasing with increasing the initial concentration. So our material having a higher affinity to absorb or remove these heavy metals and the total hardness from the water before pumping it to our system, where we study a range of concentration from 10 to 50 milligram per liter. 50 milligram, it is very high concentration with respect to the concentration found in underground water that is having a maximum range in between 20 milligram per liter. Also for the total hardness, we found the exchange capacity increasing with increasing the concentration of total hardness. That is showing a higher absorption capacity and the affinity of the prepared material to remove this material ions from the water before pumping it to our system. Okay. This is found this is Zwitterionic system. We took a real sample from Zawiya village, one of this village having these problems, facing the problems and having a high salinity and a high concentration of iron and manganese using our column system in the semi-pilot scale with certain diameter and certain flow rate and bits height. The result showing is that the removal of iron and calcium is superior with increasing the volume of treated water reach to 10 times like the volume of the prepared material, and it is very, very high with comparing it to the commercial one in the country, our country. Also, the flow rate was increasing. The flow rate is found the removal decrease due to the short tension time between the exchange and the exchange site and the ions in the solution. So the lower flow rate it is good. Also, the bed height was increasing. The bed height we found that its absorption is very high with increasing the flow rate. At the end, we use this water and pumping it using a dead end cell on certain commercial membrane, filtration membranes, and see what happened to the water and the flux under the section. As you can see, if we using our system, our membrane and pumping the feed water without any treatment, without using our composite, we found that the flux 10 liters per hour per meter square and the section 80%. But with using our composite material and combine it with our system, we found that the flux increased to 30 liters per meter per hour per meter square and the section 97. As you can see from this image, that this the first our image, it is for our own membranes without any addition of our adsorption material or pre-treatment process. So you can found the accumulation of iron sites and many scales on the surface. But if we're using our composite as a pre-treatment process for desalination for any membrane type nanofiltration or filtration, we found, as you can see, it is a clear surface. So there are a reduction in the fouling on the surface and a reduction from the chemicals used. As a conclusion, I wanted to say we synthesized a Zwitterionic composite material using titanium to formulate its structure and decreasing its capacity. This material having a high capacity to remove iron and manganese from the feed water to our OL system and the reduction of its fouling process and increasing its lifetime with time. Also, the reaction is chemosolution reaction, so it is having a higher affinity and exchange capacity. We found that is lower flow rate and bit height increasing, show a high absorption capacity for iron and the total address. Also, we found this process is good for regeneration composites and improving of our system. Also, we suggest it is well shown in the field when we design our plant in this village. It will have a higher rejection and higher flux comparing to ordinary systems. At the end, I'd like to thank our two teams. First team in Venezuela University, and they are sharing in the production of certain material having a higher efficiency and the multifunction material combined with membrane system to desalinate or treat any waste water. Also, I want to thank water desalination and the treatment groups led by Dr. Sana and my two best friends, Dr. Mohammed Shaban and Dr. Rasha, and my students, Dr. Sari, Dr. Amira, and Dr. Aya, and Dr. Sahar for their effort and scientific cooperation and discussion and bringing the product of our project in the best way. And thank you. Thank you.
Our next speaker, Professor morphology. Please, Dr. Mohammed Shaban, Chemical Engineer, Associate Professor of Physical Chemistry, Thermodynamics, Mechanical Units, Operation, Water Treatment, Test Assessment, Environmental and Statistics for Chemical Engineering, Faculty Industry Areas. Please.
Hello everyone, it's my pleasure to be here with you in this interesting event. Many thanks to Dr. Shereen for the invitation. Let's start my lecture. This is my outlines, which will be quick introduction, then speak about membrane membrane also quickly. Then I will focus about the ceramic membrane with its advantage and disadvantage. Then ceramic membrane materials and the limitations of membrane process of membrane technology. Finally, the most important topic is how to improve ceramic membrane using nanoparticle, then conclusion and references. For sure, water pollution has become one of the most significant problems at the last century due to rapid industrial growth. And for sure, water demand around the world has been increased due to increases in population growth and industrial activities. So water scarcity is becoming more of an issue. And for sure, the treatment of wastewater became necessary to protect the receiving water from any pollution and reduce the potential health risks. There are many research efforts have been done to achieve efficient strategy for wastewater use in agriculture again or in industry again. But there is still a waterborne diseases problem. This is still the main problem in any use methods. So there is many techniques can be used. Among them is membrane separations, which are powerful tools for various applications, including wastewater treatment and removal of contaminants from drinking water. We have two types of membrane. Of course, some of us know this. We have polymeric membranes and the ceramic membrane. But the ceramic membrane is preferred due to its superior characteristics for long lifetime. And also, main advantage of ceramic membrane is having capability to be used in under extremely hard or aggressive environment like acidic solution, for example. So ceramic membrane is preferred. Ceramic membrane is used from about 1960, and also it has two types: porous membrane and dense ceramic membrane. For sure, porous membrane is more better due to high porosity. The advantage and disadvantage of ceramic membrane, I think we already mentioned some of the advantages before. Ceramic membrane can be used at severe conditions like high temperature up to 280 degrees C, excellent corrosion. It has also excellent corrosion resistance and high mechanical strength. Also, it can be used under high acid or alkaline solutions, and possesses long lifetime. Finally, also it has high membrane flux for porous membrane. But also it has some disadvantage, like it's brittle, and most ceramic membranes are in disc or tabular shape, possesses low surface area to volume ratio, and this is a disadvantage. Also, its investment is probably high, or we can say the investment cost of ceramic membrane is very high. But what is the reason of the high investment? Because ceramic membrane is made from metal oxide materials. The most commonly used ceramic materials are alumina or aluminum oxide, titanium or titanium oxide, or zirconium oxide, and so on. To reach now we say on a commercial scale, the membrane are manufactured from alumina. Ceramic membrane are manufactured mainly from alumina. It can also from titanium or other oxides, but the main oxide is aluminum oxide due to its excellent structure, chemical and thermal stabilities. There are limitations in alumina membrane. Actually, two limitations. The first one is, as we said before, the cost, because alumina need high centering temperature to reach the required mechanical stress and the required size of micron size the alumina powder. So the centering temperature and the required size need high cost. So large amount of heat is required in addition to alumina powder that itself is known to be a high cost material. This is also a promising point of research because we need to find more ceramic membrane with low cost material, so we can use the clay, for example, like towel clay or another type of clay. The second limitation, which can be decreased by using nanomaterials, is fouling. Membrane or ceramic membranes can be fouled easily due to chemicals or microbes. So this limitation needs considerable attention because it can result in higher energy demand and costly cleanup for sure. There are many attempts have been made to define membrane surfaces by chemical modification. The effect is still too small to obtain satisfactory reduction of membrane fouling. So this is the second promising point of research to how to decrease the membrane fouling as much as we can. Recent advances in nanotechnology have expanded the range of application to membrane technologies. So we can use nanotechnology in improving membrane technology and to reduce fouling. The use of nanoparticles manufacturing membranes allow high degree of control over membrane fouling and the ability to produce also desired structure. And nanoparticles in the membrane can be developed by assembling nanoparticles into porous membranes or blending them with polymeric or inorganic membranes. Inorganic membranes is the ceramic membrane. Here I have 3 recent researches about using nanoparticles in improving ceramic membranes. The first one using titanium oxide, which is the next slide, but we will speak about titanium oxide, iron oxide, and maybe silicon oxide also, as we will see. Also, silver nanoparticle can be used, but it's not included here. But silver nanoparticle also can be affected then, or can be affected membrane founding. Ceramic membrane. Here is a photo for typical ceramic membranes made of layers. As you can see, we have a nanoporous layer at the top, then an intermediate layer, then macro support layer. The nano support layer can be made from titanium or titanium nanoparticles. And this study was done this year at China using titanium oxide. The study was to remove heavy metals along with vitamin B using absorption and photodegradation process, and this is a very interesting study. Due to the high removal efficiency, as we can see here, after 240 minutes, cadmium and the copper, for example, have a removal efficiency of 96 and 89%. Also the removal efficiency using photodegradation process of chromium reached 97%, which is very high percent. Another research also in the same point, the effect of nanoparticles in improving membrane founding ceramic membrane with iron oxide. Iron oxide also was used by Barati, this research at Canada, but also this year, 2021. They used ferric matrix solution to modify the membrane and to reach a modified membrane. The modified membrane used to remove humic acid from wastewater, and the removal efficiency also above 90%, and it's also considered a high percent of removal. The last research also this year was in, I think, Turkey, using zinc oxide nanorods or silicon oxide nanoparticle. Here we can see this research focused on removal of E. coli from water, and they reached almost 100% E. coli removal efficiency under pressure of 4.5 bar, and here you can see the flux of E. coli start. So here's the conclusion: the use of wastewater is considered a possible solution to wastewater scarcity. The membrane process is promising method to separate microorganisms from wastewater. The use of nanoparticles in manufacturing of membrane allows control of membrane founding and increase the ability to produce desired structure. The use of nanoparticles that have been used include titanium, alumina, silica, silver, and many others. And thank you for listening.
Thank you, Dr. Nora. Now can I open the discussion for the floor question for the first giving from our question. Please look at that.
Thank you, Dr. Nora, for the interesting presentation. And we have to say that I really what about the total dissolution effect? Have you checked the total dissolution effect?
No, for me, for my research, I focused more about heavy metals, maybe dyes like but desalination, yeah, it's not my specialization till now, but maybe after that I can.
How you clean the ceramic membrane? How you clean the membrane?
Cleaning ceramic membrane. I think ceramic membranes should be exchanged with another new one. So we said that we should use more cheap raw materials like kaolin clay. If we use kaolin clay, there will be no problem to use another one, and the waste will not be polluted will not make any pollution to environment because it's already natural source. If we use kaolin clay. But any membrane can be washed by backwash, like any filtration process.
Okay, one more question. Please.
Thank you for your presentation. The first one, why ceramic membrane has a fast power over
Alumina, due to the nature of membrane material, as we said, it is the nature of alumina. And the conventional membranes made of alumina, as we said. So we need to improve the material itself. So nanoparticles can be used to overcome this problem.
Overcome the problem of fast fouling?
Yes.
To reduce
the fast fouling.
The second one, we said that we use filling materials to surface something.
No, to reach ferric oxide from ferric nitrate. It's just a solution.
We avoid
it's just thin layer, thin porous layer, not the main component of membrane, not the main structure of membrane from. Maybe all right, but if we use a small percent or calculated percent of iron oxide, we can face this problem also.
Thank you. We will move to the next speaker.
The next speaker is engineering Ahmed, technical office and sales engineer at Signal Petroleum Service Company. Master student in Chemical Engineering Department, Faculty of Engineering, Alexandria University, Egypt.
Hello, everybody. First, I will talk about a mathematical model for controlling of thin film composite layer on the porous blended membrane. Outlines, I will discuss about introduction in the work, model development, model validation, and conclusion. As we know, there are 4 types of membrane for water treatment: microfiltration, ultrafiltration, nanofiltration, and RO. And these are different from pore size, as the microfiltration is the pore size is large than 0.1 micrometer. For ultrafiltration, take a range from 0.1 to 0.05 micrometer. And nanofiltration from 0.005 to 0.001 micrometer, and last one, reverse osmosis, less than 0.001 micrometer. These membranes can allow some particles, as we know, and prevent the other particles to pass. We have 2 steps for membrane fabrication. For manufacture of substrates, we use phase inversion technique. For polyamide layer, we use interfacial polymerization. So what is the meaning of phase inversion? It's a demixing of polymers with a solvent to convert a polymer solution to a solid, or to make a substrate. So we have 4 techniques for phase inversion: immersion, precipitation, as we see in this picture. This technique is by mixing polymer solution and spread it on a flat sheet or on a plate, then immerse the plate in non-solvent or in water to make a substrate, and then it driven by atmosphere. Thermal induced phase separation by lowering temperature. Evaporation induced separate by evaporate a solution of solvent and non-solvent to evaporate a volatile solvent solution. First technique is a vapor in which placing cast film in a vapor phase contain a non-solvent solution. So the most common technique is immersion precipitation for make a substrate. For make artificial polymerization, artificial polymerization is the most important technique in a commercial fabrication of thin film composite layer. Mostly take place in elevation osmosis or in a nanofiltration membrane, and the commonly polymer used is metaphenylene diamine with trimethyl chloride, and also we can use a polymer vibrazine with isophysiloid chloride and hexane, vibrazine with trimethyl chloride and hexane, 1,2-ethane ethane diamine with disulfonide chloride and chloroform, and carbon tetrachloride. This picture is illustrate how the interfacial polymerization takes place, as we have two monomer A in a reaction zone or in support membrane, monomer B in organic zone, and monomer A will diffuse to the surface of the membrane and take a reaction in the reaction zone sigma between the monomer A and monomer B in organic solution. So the polyimide layer will form in the interface of the membrane. Aim of the work, to development and verification the mathematical model for thin film growth layer membrane by interfacial polymerization, by verification of the model development by using lapis scale, modification and development of the fabricated ultra filtration by polyether sulfon, and polyacrylonitrile blended membrane in which polyamide selective layer is introduced on the borders of the blended membrane by using vibrazine and isophysiloid chloride. Last, by using MATLAB code or software for solving second order partial differential equation. Model development. A general model has been investigated for synthesis of thin film composite flat sheet membrane by diffusion and reaction controlled interfacial polymerization. First, we make some assumptions before make a model, as we put as the system is considered in the interfacial polymerization of monomer A and in the aqueous support, in the aqueous solution and support membrane, and monomer B in the organic phase. The newly formed polymer doesn't dissolve in either organic or in aqueous phase, and the density of the thin film is uniform during the reaction. Last assumption is the reaction will take place at sigma at the reaction zone, as we said before in this picture. So for solving the relationship between polymerization time and thin film thickness of the interfacial polymerization, we use this equation. This equation developed in which X is the thickness of the thin film, phi p is the volume fraction of the thin film and also can be calculated by the equation below. Mu is the average molecular weight, rho W is the density of the water, P is the density of the polymer, and beta is the molar ratio of the water to monomer A transported together by diffusion. Ki is the constant and also can be calculated by the equation the right. Kr is the second order reaction rate. Sigma is the reaction zone. Mu, as we said, is the molar molecular weight or molar mass. And rho P is the density of the polymer. Finally, we put these equations in the main equation of the X. And C node is the initial concentration of monomer A, Cp is the concentration of monomer B, and C is the polymerization time. And from this equation, we get the relationship between polymerization time and the thickness of the thin film. To calculate also the relationship between polymerization time and growth rate, we can use this equation in which R is the present growth rate of the thin film. A node, B node, C node, D node, and E node are constants and also can be calculated by this equation in which Dm is the effective diffusion coefficient, Ki is the constant, Cp is the concentration of monomer B, C node is the initial concentration of monomer A, Fl is the fraction of A that diffuses out the top of the support membrane and take a range from 0 to 1. K is the partition coefficient of monomer A between the support and the thin film phases. Also, the other parameters or the other terms are we discussed before. So we substitute these constants in the main equation to get a relationship between R and time, the polymerization time and the growth rate. Last equation to calculate the monomer concentration. All of these terms also we discussed before. By using the first equation of thin film composite, we can make a comparison between different polymerizations. So we calculate the thin film thickness, the polymerization time, and the polymerization time for biprazine with isophenylate chloride, hemiphenylene diamine with trimethyl chloride, biprazine with trimethyl chloride, 1,2-ethane diamine with trimethyl chloride. We found that the thickness of the thin film of hemiphenylene diamine with trimethyl chloride, which present curve B, increase with time, and the thickness will reach 0.2 after 1.5 seconds. For curve D, which presents 1,2-ethane diamine, will reach to 0.2 micrometer after 1.9 seconds. 0.2 micrometer is the ideal thickness of the film, the good layer. With increasing time, we found that curve B and curve D will decrease rapidly. And while curve A and C, which present biprazine with isophenylate chloride and biprazine with trimethyl chloride, continue to increase with time. And biprazine with trimethyl chloride, curve C, will reach thickness 0.2 micrometer after 10 minutes. Curve C will reach 0.2 after 4 minutes, and while the bibrazine with isophysalyl chloride. Curve A will reach 0.2 after 10 minutes. So, bibrazine and trimethyl chloride, bibrazine and isophysalyl chloride will take a long time to form a good layer. Model validation, we set an experimental to prepare interfacial polymerization and polymeric membrane by using 0.1 weight percent isophysalyl chloride and 2 weight percent bibrazine in normal hexane, and prepare polymeric membrane by using 14 weight percent polyether sulfur with 4 weight percent polyethylene glycol and 1 weight percent polyacrylonitrile, which dissolve in 1-methyl-2-pyrrolidine and annealed at 5 minutes for 5 minutes and at 80 degrees Celsius, and soaking the membrane for a different time, 10 minutes, 15 minutes, and 20 minutes. The results we see for membrane soaking time 10 minutes, the thickness will be 0.168 micrometer. For 15, the thickness will be 1.99 micrometer. For 20 minutes, the thickness will be 0.295 micrometer, which is which increasing the time the thickness will increase, as we said in the membrane morphology. Membrane morphology. By putting the actual results in a theoretical model, which we calculate, we found that there is a small deviation between the theoretical model and the actual results. So, conclusion, we conclude that under non-steady state condition, the theoretical model predicting both diffusion and reaction controlled interfacial polymerization thin film composite membrane has been created. The mathematically applicable to any types of interfacial polymerization. In the early stage of the polymerization, the thickness of the thin film produced by interfacial polymerization rapidly increased, then leaves off. The model has been validated using actual data, and the results show good agreement with the real data. Thank you.
Time factor as a factor. How to stop the action? So you have to control the action after 10 minutes, 15 minutes, 20 minutes. You see.
هو يعني بنقيس التايم يعني بوقف الرياكشن، وانا بعد تايم معين بحسب هو الثيكنس وصل قد ايه. بعد كده يعني ده الاكتوال نفس الكلام. الكيرف اوريدي هو بيرسم ريليشن بين تايم يعني بتسال على الاكتوال اللي بيحصل، صح؟ هي الفكره انه افتر تايم معين انا بوقف التايم بحسب رياكشن حصل دلوقتي الثيكنس ظهر قد ايه، مش بكنترول فيه واقول ان التايم الرياكشن وقف.
قاعد دكتورة قاعد دكتورة
اوكي شكرا.
Teaching assistant of material and energy balance, the action engineer is the equilibrium and the bioprocess engineer at environmental engineering department, Zwitterionic University, master student in chemical engineering department, faculty of engineering, Kamel University. To speak about review on geopolymer membrane preparation for water treatment application.
Hello, everybody. Firstly, I want to thank Dr. Shereen for giving me this opportunity to attend and participate in this conference. I think I'm the youngest one in the speakers, so please be kind with me in the questions. Okay.
Don't worry, you are just stage of comment. You are the smallest one and the newest one in the state.
Okay. I'll give you an introduction just to enlighten you about geopolymer, its preparation and applications. So, what's geopolymer? Geopolymer is an aluminosilicate-based inorganic polymer. It's formed by heterogeneous reaction between aluminosilicate solid source and concentrated alkaline solution. This reaction is called geopolymerization reaction, which is polycondensation polymerization. Note that aluminosilicate sources are the most abundant in the Earth's crust. That's why we called it geopolymer. Geopolymer has three basic forms, depending on silicon to aluminum ratio, namely polysilicate, polysilicate siloxo, polysilicate disiloxo. This is sialate group, SiO-ALO, and this is siloxo group, SiO. So it's obvious that in polysilicate, we have silicon to aluminum ratio equals 1, and in polysilicate siloxo, we have silicon to aluminum ratio equals 2, and in polysilicate disiloxo, we have silicon to aluminum ratio equals 3. If the ratio is greater than 3, then we have sialate link, which is cross-linked polymer. The microstructure of geopolymer is amorphous to semi-crystalline, that's temperature dependent. Geopolymer has a lot of advantages that make it suitable for a variety of applications. Generally, it has low manufacturing cost because of the simplicity of its preparation. It has good physical and mechanical properties. It also has some criteria that make it suitable for specific applications. The first and second criteria are low energy consumption and reduced greenhouse emissions. These two criteria make it a good replacement of Portland cement because in the calcination process of cement, the calcination of lime, it emits CO2, but the calcination of aluminosilicate source doesn't emit CO2. The third criteria is anti-corrosion, which make it can be used as storage for chemical. The first one is fireproof, so it can be used as fire and heat resistance coating. The fifth one is high porosity, which make it used as membrane. As I mentioned, we have solid source raw materials and liquid source raw materials. That's why we have heterogeneous reaction. The solid source includes clays like metakaolin and industrial waste, for example, ashes, slag, waste blast, copper mine tailing, rice husk, etc. Of course, metakaolin is more expensive than industrial waste, but it's preferred because it allows easy interpretation of results, because it doesn't contain impurities like industrial waste, so it's preferable for membrane preparation. Liquid source is called alkali activator. It includes alkali hydroxides and alkali silicates, but it's better to use mixture of both alkali hydroxide and silicates. The preparation technique consists of mainly 2 steps. The first one is mixing of solid and liquid raw material sources, and if we have additives, we will add it also to form binder. Then curing to consolidate this binder to form hard geopolymer. There are some additives added to the main raw materials to enhance some properties according to the application. So here in membrane preparation, we have main additives: hydrogen peroxide, which is a foaming agent that we added to enhance porosity. Zeolite, which has double effect because it enhances the porosity because it has microporous structure, and it also increases the compressive strength if it ends as fine particles with small ratio. There are some factors affecting the properties of geopolymer. The first and the most important one is the pre-treatment of raw material. It's found that geopolymer produced from calcined raw materials like metakaolin, ash, and slag shows better mechanical properties. Previously, they used kaolinite, but the geopolymer was weak, so it was calcined. Calcination also helps to improve the reactivity of raw materials, transforming it from crystalline phase into amorphous reactive phase. Also, curing temperature and water content, in addition to the additive, can control the porosity and the pore size of the geopolymer. That's it. Thank you.
Best, from my opinion, the best one, but you say everything very clear, quickly, but very clear. I want to go to any question. I think لا هي بتسأل هي برضه هي محمسة هي ده شباب بسم الله الرحمن الرحيم اتفضل.
هو ماذا استخدام مصر يعني وصلنا كتير؟
ماذا استخدام الجيوبوليمر وصلنا كتير؟
اوكي، هو المفروض ان هو حاجه حديثه، فيعني اصلا كل البيبرز بتاعته تقريبا ستارتنج من 2010، فمش يعني تقريبا 2010 يعني مش قديم قوي. مش عارف يعني اول بيبر مثلا.
هو هستاذن حضرتك بالنسبه لمصر جيوبوليمر هو دخل الحديث في الابحاث وفكر بدايته في استخدامه كمواد بناء كبديل لمواد البناء وكطوب بالاخص كطوب للبناء بدل من الطوب الاحمر اللي بيستخدم حاليا. وده احنا عملنا فيه ابحاث كتير ودخلنا منه باستخدامات بعض المخلفات المصانع برضه دخل وانشانا منه طوب بناء واعطى نتائج جوده مطابقه للمواصفات القياسيه المصريه والامريكيه في مقارنه بالطوب المستخدم حاليا اللي هو الطوب الاحمر. تمام؟ بالنسبه للممبرين هو لسه سيرش حديث بدأ في سنة 2020 أو 2019 الماكسيموم في مستوى العالم على مستوى العالم، ولسه حديثا بيستخدم في كممبرين أو كمواد أبزوربنت لبعض المواد الملوثات الموجودة في المية. شكرا.
شكرا دكتورة شيرين، شكرا دكتورة